Hello, everyone. Now let's begin with today's lecture. So first, we are going to talk about the homework assignment. And last time I assigned the homework number 9. So this is a kind of difficult problems, okay? So I'm going to guide you through. So here we'll talk about sequence, which is bounded, okay? So this is the assumption. Now we have a very strange assumption, saying that every converging subsequence is converging to the same limit L. And you're asking to use the BW theorem to show that the Xn itself is also converging to L. So what we want to do here is we're trying to use the method of contradiction. Now, how do you begin with this contradiction? So you first suppose that your conclusion is not true. So assuming conclusion is not true, this means that you're assuming Xn does not converge to L. So if Xn does not converge to L, so there must be a spatial epsilon greater than 0, such that for any k, there is a large enough index nk greater than k, such that the absolute value of x and k minus L, so this is the distance between the term and the limit, okay, is greater or equal than epsilon naught. Okay, so this is the actually follow from a theorem 2.4 we studied before. It's called non-convergence. So it means that if limit xn does not equal to x, so what happens? So we are basically copy the result of this theorem. So if we use the method of contradiction, so we begin with this using this argument, okay, assuming xn does not converge to L, so there must be an x naught, the epsilon naught set by all these, okay? So now let's see how we can go from here to get a contradiction. So next step, okay, now you are focusing on the subsequence. So the previous statement saying that for each k, there is a nk, right? So correspond to this special index nk, you are forming a subsequence, x and k. So for this subsequence, it satisfies that the x and k minus L is always greater than or equals to epsilon naught. So this subsequence is actually away from this L, okay? And then you can see that this subsequence cell is also bounded. So therefore, by the BW theorem, okay, saying that the theorem says that every bounded sequence carries a convergent subsequence. Okay, so this means that looking at this subsequence xn naught, there is a subsequence of this subsequence which is convergent. This is guaranteed by the BW theorem because the subsequence xnk itself is a bounded sequence. But BW theorem says that this bounded sequence must carry a subsequence. So we're talking about subsequence of subsequence, which is convergent. Okay, so so we can denote this. So how do we denote the subsequence of subsequence? We have used a complicated symbol. So we can call this subsequence is X and K L. Okay, so there's a 3-letter in the index, just indicating that it's a subsequence of subsequence. Okay. Okay, so this subsequence cell, the subsequence of subsequence is convergent. But based on our theorem, all subsequence goes to L. So this subsequence of subsequence, which is of course, a special subsequence of the original sequence, should also goes to L. So X and KL should converge to L, okay? And then you can see that this will contradict because that from the definition of NK, the absolute value of X and K minus L is greater than or equal to epsilon naught. And the X and KL itself is just a subsequence. Of course, itself will satisfy the same estimate. Okay, so this means that S and KL minus L is also away from L. So this contradicts to the fact that the X and KL cell is converging to L. So this contradiction saying that the very beginning, the initial assumption is wrong. Okay, so this means that Xn itself must converge into L. So that's the way to solve this problem. You have to think about it, trying to fully understand this argument. Okay, and maybe you can apply the same idea to some other cases, right? And actually, in a later chapter, we are going to use some similar idea here. Okay, so this is about the homework problem number 9. Now let's continue. So today we're going to end chapter 2. So now let's, last time we talked about the Cauchy sequence, right? We also seen 3 examples. Now we want to work more on the Cauchy sequence, okay? So let's begin with the theorem 2.11. Okay, so first we're going to see that so our goal is to show that a sequence is convergent if only if it is a Cauchy sequence. Okay, so this Cauchy sequence is a necessary and a sufficient condition for a sequence to be convergent. Okay, but here we're going to first prove the easy part. So we're going to show that if you have a sequence, we know it is convergent, then we're going to show that the sequence is a Cauchy sequence. And later, we're going to prove the other side. We're going to show that every Cauchy sequence will also be convergent. Okay. Okay. Now this is an easy part. So let's say that the sequence cell is converging. So this means that the limit, we can assume the limit xn equal to x. Okay. So then we apply the limit definition. So this means that for every epsilon greater than 0, so there is a positive k to make this happen. But we are not going to put epsilon. We want epsilon divided by 2 for a technical reason. So this means that as long as n is greater than k, this is going to happen. So now let's choose in 2 index, n and m, both greater than k. And then you have, they both will satisfy the same thing, right? So therefore you can estimate the distance between xn and xm. So you can just using the regular technique, inserting x minus x plus x into it. And then you cut in the middle using triangle inequality. So you can see everything controlled by xn minus x plus xm minus x. And both are less than epsilon divided by 2. So total is less than epsilon. So this way we verify that the we just verify that the sequence, it is a Cauchy sequence. So this shows that for every converging sequence, the sequence has to be Cauchy sequence. Our goal here is to show that every Cauchy sequence is also a converging sequence. So that's why convergence is equivalent to the Cauchy condition. Okay, so in order to get there, we need to prepare something. So that's the next theorem. It's called the boundedness of Cauchy sequence. Now this is a similar theorem as we studied at the very beginning about the limits, the limit property. So we show that if a sequence is convergent, then the sequence has to be bounded. So what we're going to show here is that a sequence, if a sequence is a Cauchy sequence, then it is bounded. And the proof is very similar. Okay. So let's say that you have xn, which is Cauchy sequence. Okay. So now let's choose epsilon equal to 1. Apply the limit definition. So then you can see there exists k such that now this time you are not assuming xn is a converging sequence, it's a Cauchy sequence. Okay. So we are using apply the definition of Cauchy sequence. And so there is it k such that for both n and m greater than k, now let's assume that n is greater than m. Then the distance xn and xm is less than 1. Okay. So in particularly, okay, so you fix this k, okay, you look at a term xn compared to the term xk plus 1. Now k plus 1, you can treat it as m because k plus 1 is greater than k. Right? So you can treat it in m. So you can see that xn minus xk plus 1 is less than 1. So this is true for all n greater than k, right? So for general n, okay, you can see that so you look at the value of xn itself, absolute value of xn, and this absolute value can be estimated through the previous estimate. What you do is you just insert the minus xk plus 1. Now here's a typo, okay? Then you plus x k plus 1. Then you use triangle inequality. So the whole thing is controlled by xn minus xk plus 1 absolute value plus the absolute value of xk plus 1. So you can see that the xn, so the absolute value of xn can be controlled by 1 plus the xk plus 1. Now remember, the k is fixed. So here, the right side is some kind of fixed number. It's a fixed, okay? The left side, the xn, then the index can change, okay? You can choose any n greater than k, but no matter what n you choose, the absolute value of xn is always controlled by this fixed number. So therefore, for all the n, okay, so you can see that the size n is greater than k, then everything is under control. But before k, there's still a finite number of terms, right? But then you can add all these finite number of terms into the maximum, okay? And you choose the maximum of all these. Obviously, they control all the terms for all n. So this just shows that the xn is bounded. So proof is very similar to the proof for the converging sequence, okay? So that's the first thing we need to prepare. The another thing is we need to prepare is that now, okay, so now let's go on to the stage, the final stage. So here we want to show that a sequence xn is converging if only if it is a Cauchy sequence. So this is the theorem we want to prove, and we have finished the first half, right? If side is basically the proof of theorem 2.11. Now we're going to prove only if side. So let's assume that xn is a Cauchy sequence, and we want to now see how we can prove it is converging sequence, okay? So first, by the theorem 2.12, we know that it is bounded because it's a Cauchy, okay? So therefore, if you have a bounded sequence, so the first thing you want to think about how to use BW theorem. So apply the BW theorem on this bounded sequence, you can see that since this Cauchy sequence is bounded, so even though I don't know this Cauchy sequence is convergent, but I do know that there is a convergent subsequence. So at least I can get a subsequence which is convergent. Okay, of course, that's not enough. So we're going to see that how we can show that the original sequence is also convergent. So let this converging subsequence be xnk, which is converging to a limit x, okay? So now we're going to show that the original sequence xn is also converging to x. Okay, so let's begin with argument, okay? So for every epsilon greater than 0, so there exists a positive integer k such that when both n and n greater than k, the distance between xn and xm is less than epsilon to r2. Now here, what we put here is just a definition of Cauchy sequence, nothing else. Okay, nothing else. Now, in the next step, we're trying to work with the subsequence to see how we can combine the previous result about the subsequence with this to show that the sequence is actually a converging sequence. So, proof continues. Now, since the subsequence xnk is convergent with a limit x, so one can choose k large enough so that nk is greater than k, okay? And that's the xnk minus x is less than epsilon divided by 2. Now here, what we're doing here is that since the subsequence is convergent, so I'm applying the limit definition on the subsequence. Okay, so therefore, for this epsilon divided by 2 correspond to this epsilon divided by 2, there's a k exists. So as long as nk greater than this capital K, so this estimate works, right? Then you can go to the next step. So you look at the xn minus x, the absolute value. Now using the usual technique, making connection this with the subsequence by inserting x and k into it. So minus or plus, they cancel. Then you use triangle inequality to cut in the middle. So you can see that xn minus x absolute value is less than or equal than xn minus xnk plus xnk minus x. And you know that both terms on the right side are less than epsilon divided by 2. So this is epsilon. So this is the way we show that xnk. So it's a typo. Xn itself is converted to x. So this finished the result. Now this is a very important result. It's showing that the sequence carries a limit if only if the sequence is a Cauchy sequence. Okay. So this is the end of chapter 2. Okay. So as we decide already, and we're going to have a chapter 2 quiz next Thursday. Okay. And next Tuesday we'll begin with chapter 3. And we'll make sure that I'm sending you the notes before that. Okay. And so use your weekend to prepare for the chapter 2 quiz. And last time I have already tell you what kind of problem will be involved in the chapter 2 quiz. And you just review these problems and study these problems, they'll be sufficient. Right? Okay, so this is today's lecture. Thank you.